a PhD student from Cardiff University, and because I'm from Cardiff, I look at dust with Herschel. So specifically, we've been looking for dust in galactic remnants. Okay, so we've already had a lot of detail from Rubina about the supernova dust debate. But just to reiterate, from theory, we expect that supernovae can produce a substantial mass of heavy metals. And in several studies, there's been detected significant masses of dust in supernova remnants. But we don't really know how much of that dust can survive destructive processes, and if it does survive, then what does it look like afterwards? So really we need a larger sample of dusty remnants to look at how factors such as the environment, the progenitor type and the age affect the survival and the type of dust. So we've been putting together a catalogue of dusty remnants from our galactic plane using data from HiGal, which you can see at the bottom of there. And we're looking for any evidence of dust in remnants. We've looked at 190, and we detect around a fifth of our sample. Of those, there's 3 that are of particular interest to us, because we think that they are new detections of ejecta dust. So we've estimated the mass of the ejecta dust in those sources using 2 methods. So first of all, with a traditional SED fitting, and then with a more rigorous method called point process mapping. So this allows us to look at the distribution of the mass across the source and also across different temperatures and emissivity indexes. So we can study the property of the dust as well as the temperature. So the first stage was to produce this catalogue. So we've got this example here. So we've got a Herschel 3-colour image. And we're looking for any structure that stands out from the surrounding medium. So we've got this filament and shell of warmer dust than the surrounding ISM, and that correlates really well with the MIPS 24 micron structure, and also with the optical double shell that we see here. So that confirms that this is a good detection of this source. We do a similar analysis for 190 sources across our galactic plane, and we detect a fifth of those. Because we're looking at the galactic plane in the far infrared, not all of our sources are as clear as the one I showed. So we have some very clear detections, but also you can see outlined in pink and in grey that in some cases we just can't pick out any structure from the surrounding ISM. So it really highlights the point that although we detect a fifth of our sample, that is a lower limit on the number of sources that might contain dust. A lot of our sources aren't very well studied, but those that are, we detect 2 type 1As and 14 core collapse supernovae. We're also biased towards detecting sources where there's warmer dust than the surrounding medium. So that might be because of shock heating or a pulsar wind nebula. Okay. In most cases, we expect that the dust isn't necessarily associated with the supernova explosion. So it's dominated by dust that's been swept up from the ISM or associated with the cloud that's been heated by the expanding remnant. But there's 3 cases which are interesting to us because in each case we detect this central region, which is really bright at 70 micron. And in these 3 cases, it's coincident with a pulsar wind nebula. So in these 3 sources, we expect that the wind nebula is heating ejecta dust in those regions. G11 is particularly interesting to us because it's thought that the reverse shock has already reached the center of the source. And so any dust that we detect in this central region has survived the passage of the reverse shock. So having detected ejecta dust, we want to know how much there is. So we first do this with an SED fitting routine. So you can see our SEDs here. And that gives us the temperatures and masses in that table. So in all 3 cases, again, we're looking at this wind nebula region. And we estimate temperatures that are warmer than the surrounding ISM, and in all three cases we estimate a significant dust mass. For G11, this is quite large. We think this is slightly overestimated because of some contamination from the background ISM. And for KES 75, we're unable to constrain that because of uncertainty associated with the background. So similar to what Rubina was talking about. But in the case of G21, we're able to constrain this mass quite a lot, and we estimate a significant dust mass for that source. For our SED fitting, we have to assume that all the dust has just one or two temperatures and just one emissivity index, so all the dust is the same, which we know isn't realistic. So we go on to use a more rigorous method called point process mapping. And this uses a Bayesian analysis over a series of steps to allow us to look at the distribution of the dust across the source and also across different temperatures and values of beta, so that we can look in more detail at the properties of the dust. We give PPMap 6 images between 24 and 500 micron, and it returns a 4D grid to us of column density across the XY plane of the source, across temperature, and across beta. So first of all, we collapse our 4D grid into a set of images like this, where each image shows the column density across the source at a different temperature. So we start up here at 20 Kelvin and then move to the bottom right at 90 Kelvin. So the first thing we notice is that when we use PPMap, we can detect dust as cool as 20 Kelvin in our source. So with our SED, for this source, we estimate an average temperature of around 27 Kelvin. So this much cooler dust might affect our dust mass estimate quite a lot. The other thing we notice is that when we looked at Herschel, at the 3-color image, it just looked like the source was a blob of dust. But when we look with PPMap, we can detect more detail in the structure. So we see this cool peak at cooler temperatures, and then as we move to warmer dust, we see this shell emerging around the southwest of the source. So we can make out more detail because PPMap allows us to look at these sources at the resolution of the Herschel 70 micron. So that's a lot better than we can look at the temperature maps using traditional SED fitting. We can also study the properties of the dust. So in a similar way, if I just flip back, we can collapse our 4D grid to get a grid of maps for column density, where each image will show the column density across the source at a different value of beta. And then we can use that to compare different regions. So we use a method similar to aperture photometry. So we put an aperture around our ejector region, and we add up all of the column density in that region, and then that gives us these points on here. And then we do the same with an annulus to represent the surrounding ISM, and that gives us the black points on this graph. So the main thing we're interested in from this graph is the location of the peak, and that tells us the value of beta for the majority of the dust in that region. So for the surrounding ISM, we see that the beta has a value of around 2 to 2.5, whereas for the ejector, the peak is at a slightly lower value, which seems to suggest that the properties of the dust in the ejector are slightly different to the ISM. We do have to be slightly careful with this because our error bars for the ejector are quite large, but we think that with high signal to noise or longer wavelength data, we could really constrain this to see if it's a real effect. So the final thing we can do with PPMap is to look at the mass of the dust in these sources. So again, we're looking at the wind nebula regions in these supernova remnants. So looking first at G11, we estimate a slightly lower, well, a much lower dust mass with PPMap than we did with our SEDs. So we think that that's partly because we can probe different temperatures with PPMap. So when we looked at the cooler dust temperatures, we noticed that the dust didn't seem to be associated with the remnant, and so we could exclude that from our dust mass estimate. For the other two sources, we estimate quite a lot larger dust masses, especially for G21. And again, this is because we can look at a lot of different temperatures with PPMap. So we see dust in these sources as callers around 20 Kelvin, whereas with our SEDs we estimated temperatures of around 27 to 30 Kelvin. So those caller dust components add quite a lot of dust mass to our estimates. So in all three cases, we expect that the PP map results are more reliable, and for all three sources, we estimate significant dust masses with that method. So to conclude, we've completed a catalogue of dusty remnants within our galactic plane, and we add 41 sources to the current sample. Of those, 3 are particularly interesting to us because we think they're new detections of ejector dust being heated by a pulsar wind nebula. And in all 3 cases, using 2 different methods, we estimate a significant dust mass. We find in one source that there's marginal evidence for a variation in the dust properties between the ejector and the surrounding ISM, but we really need longer wavelength data or higher signal to noise to constrain that. So thank you for listening.
Thank you, Hannah, for a really nice talk. Are there any questions?
What sort of sizes of dust are you inferring?
We haven't looked in detail at the size distribution of the dust, but they're around micron sizes.
Micron sizes?
Yeah.
I mean, when you look at meteorites, there's chondrules in them which seem to predate the solar system. How are they formed? They're millimetric, 1,000 times bigger.
I wouldn't be able to answer that question. I don't know if someone else can give you an answer for that.
Well, one possible answer is that there are assemblages of dust, smaller dust grains that are fused into larger chondrites.
Any other questions? Got time for one more quick one. Okay, I have one very quick one. I'm interested to know if the PP map process, which seems to be much more sophisticated than traditional SED fitting, could that be applied to extragalactic supernovae, or does it require having the spatial resolution?
So we found that we really need the resolution. So even with our resolution, we can't really tell much difference between the properties of the dust. So it would be quite difficult. It's been applied to extragalactic galaxies, but I'm not sure if it could be to extragalactic remnants.
Let's thank Hannah again.